America's largest reservoir continues to retreat, leaving behind an unmistakable white mineral band along its steep canyon walls that reveals just how far the water has fallen over the past 2 decades. Every decline in elevation raises another question for the American Southwest, where millions of people depend on the Colorado River for drinking water, agriculture, and electricity. As Lake Mead inches closer to historically low levels, one of the most expensive water infrastructure projects ever undertaken by a single American city has become the center of attention. A tunnel costing approximately $1.5 billion now reaches deep beneath the reservoir, extending to water levels that were once considered almost unimaginable. The project represents an extraordinary engineering achievement, but does it truly protect the region from an increasingly uncertain future? Or does it simply buy valuable time while the reservoir continues to shrink? Unlike many emergency projects that begin after disaster strikes, this massive tunnel was conceived years before Lake Mead reached today's critically low elevations. Engineers and water managers recognized that if the reservoir continued to decline, Las Vegas faced an alarming possibility. The city's existing water intake structures, which had reliably supplied southern Nevada for decades, were positioned at elevations that eventually could become unusable. If the lake dropped below those intake openings, the city's ability to withdraw water would become increasingly limited, regardless of how much water remained elsewhere in the reservoir. That realization fundamentally changed the way planners viewed the future of Lake Mead. For decades, Hoover Dam successfully transformed the Colorado River into one of the most dependable water storage systems in the United States. Completed during the 1930s, the dam created Lake Mead, which at full capacity stores approximately 26.1 million acre-feet, equivalent to nearly 32.2 billion cubic meters of water. The reservoir became the principal source of water for cities including Las Vegas, Phoenix, Los Angeles, San Diego, and Tucson, while also supporting agriculture across the desert Southwest and generating enough hydroelectric power to supply more than 1 million homes. Few imagined that one day the greatest challenge would not be storing water, but reaching what remained of it. Since the year 2000, Lake Mead has declined by approximately 160 feet, or nearly 49 meters. Today the reservoir holds only about 30% of its maximum capacity, containing approximately 8.3 million acre-feet, or about 10.2 billion cubic meters of water. The striking white bathtub ring surrounding the lake has become a visible reminder of that enormous loss. As the water continued falling, engineers identified a serious vulnerability. Las Vegas depended on intake pipes extending into Lake Mead, but those pipes had been constructed when reservoir levels were expected to remain much higher than current conditions. If declining water eventually exposed those intake structures or left them above the usable water line, Southern Nevada's primary water supply would face severe operational challenges. Rather than waiting until the problem became an emergency, the Southern Nevada Water Authority chose a different approach. It approved what became known as the Third Intake Project, one of the most technically demanding municipal water projects ever attempted in North America. The investment eventually reached approximately $1.5 billion, reflecting not only the scale of the construction, but also the extraordinary engineering required beneath one of the nation's largest reservoirs. Building another intake pipe near the shoreline was never an option. Engineers needed to reach water that would remain accessible even if Lake Mead experienced declines well beyond previous historical records. The solution required constructing an entirely new tunnel deep beneath the lakebed. Excavation began through solid volcanic rock using a specialized tunnel boring machine designed to operate under intense underground pressure. Unlike conventional tunnels passing through dry terrain, this project advanced beneath an active reservoir while maintaining exceptional precision over several miles. Every section had to withstand enormous geological stresses while preventing water infiltration that could jeopardize construction. The engineering challenge became even greater because the tunnel needed to connect with an intake shaft located beneath the lake itself. Workers completed this connection while surrounded by immense hydrostatic pressure, generated by hundreds of feet of water above them. The final breakthrough represented one of the most difficult underwater tunnel connections ever completed for a municipal water system. The finished tunnel extends to an elevation of approximately 875 feet, or nearly 267 meters, above sea level. That number is far more significant than it first appears. Hoover Dam reaches what engineers call dead pool at approximately 895 feet, or around 273 meters. At that level, water can no longer flow through the dam under the force of gravity. Downstream deliveries would effectively stop because the reservoir would sit below the outlet structures needed for normal operations. The third intake was intentionally built approximately 20 feet, or around 6 meters below that threshold. In practical terms, that means Las Vegas can continue withdrawing water from Lake Mead even if the reservoir falls below the point where Hoover Dam itself can no longer release water downstream through gravity. Massive low lake-level pumping stations lift water from the deep intake into the city's treatment facilities before it enters Southern Nevada's distribution network. Without those pumps, gravity alone would no longer be sufficient. The pumping station itself became another major engineering accomplishment. Its enormous pumps were specifically designed to operate under conditions that previously had never been anticipated when Hoover Dam and Lake Mead were originally constructed. Together, the tunnel and pumping system created an entirely new method of accessing the reservoir during extreme low water conditions. This infrastructure dramatically strengthened Las Vegas's water security. Unlike many other communities depending upon Lake Mead, Southern Nevada now possesses the ability to continue drawing water long after older intake structures would have become unusable. Combined with aggressive conservation measures and extensive water recycling, the city has significantly reduced the immediate risk of losing access to its primary water supply. That preparation reflects decades of planning rather than a last-minute response. Southern Nevada has reduced per capita water consumption by approximately 55%, even while adding more than 800,000 new residents. More than 250 million square feet, or roughly 23 million square meters of decorative grass has been removed, saving an estimated 203 billion gallons, equivalent to approximately 768 billion liters, of water. Nearly all indoor water is collected, treated, and returned to Lake Mead, allowing it to be reused instead of permanently consumed. These conservation efforts work alongside the tunnel rather than replacing it. Yet despite its remarkable engineering, the $1.5 billion project cannot solve the central problem facing Lake Mead. The tunnel provides access to water. It does not create additional water. Every gallon pumped through the system still comes from the same shrinking reservoir. If inflows continue falling while withdrawals exceed replenishment, Lake Mead will continue losing storage regardless of how advanced the intake system becomes. The reservoir's decline ultimately reflects conditions affecting the entire Colorado River Basin. The river was divided under legal agreements negotiated during unusually wet decades, allocating approximately 16.5 million acre-feet, or nearly 20.4 billion cubic meters, of water annually. Modern measurements indicate the river now averages substantially less than those historical estimates, particularly since the beginning of this century. At the same time, rising temperatures have increased evaporation, while reducing Rocky Mountain snowpack, leaving less runoff available to refill Lake Mead. Agriculture continues consuming roughly 70% of Colorado River water, while growing populations maintain pressure on limited supplies. The tunnel cannot change any of those realities. Its purpose is resilience rather than restoration. Federal agencies are pursuing similar strategies at Hoover Dam itself, by replacing older turbines with new wide-head designs capable of generating electricity down to approximately 950 feet, or nearly 290 meters, above sea level. Like the tunnel, these upgrades extend the operating life of existing infrastructure without increasing the amount of water available. Engineering is allowing critical systems to function under conditions that previous generations never expected. Even so, the long-term future of Lake Mead will depend on balancing water demand with the river's actual supply, rather than the larger volumes envisioned more than 100 years ago. The $1.5 billion tunnel beneath Lake Mead stands as one of the most sophisticated water infrastructure projects ever completed in the United States. It protects Las Vegas from a threat that once appeared almost unavoidable and ensures that the city can continue accessing water under reservoir conditions that would disable older intake systems. It represents remarkable foresight, exceptional engineering, and years of careful planning. At the same time, its limits are equally clear. The tunnel is not a rescue for Lake Mead itself. It cannot refill the reservoir, increase Colorado River flows, or reverse decades of declining storage. Instead, it serves as an insurance policy, one that keeps water flowing to southern Nevada, while the much larger challenge of reducing demand across the Colorado River Basin remains unresolved. In that sense, the $1.5 billion investment has already achieved its immediate objective. Whether it ultimately proves sufficient depends not on the tunnel alone, but on whether the reservoir above it can continue holding enough water to pump.